This is an animated video abstract for our article titled Fermat's Polygonal Number Theorem for Repeated Generalized Polygonal Numbers, appearing in the Journal of Number Theory. A polygonal number, or specifically, an m-gonal number, is a non-negative integer that can be represented by a regular polygonal arrangement of points on the plane. For example, look at the following sets of triangular numbers. A polygonal number, for m greater than 3, is given by the following formula. Let's look at some history related to these class of numbers. A conjecture of Fermat dating back to 1638 states that every positive integer may be written as the sum of at most m m-gonal numbers. Specific cases of this conjecture include the Lagrange's 4 squares theorem and Gauss-Eureka theorem, which are pretty well known. Since Cauchy resolved the general case in 1813, Fermat's polygonal number theorem has been generalized in many directions. Fermat's conjecture precisely asks you to look at this problem of universality. Given any non-negative integer n, will a solution to this equation always exist? And if it does, how many terms will you need at minimum? We are interested in the universality of this following sum of generalized polygonal numbers, as well as the minimality of L, the number of terms used. By the theorem of Fermat and an argument of Guy, it is evident that for m greater than or equal to 8, RL can be bounded in this small gap between m and m-4. We investigate where the true answer lies in this gap, and show that in the case of generalized m-gonal numbers, L is exactly equal to m-4 for m greater than or equal to 10. This is our first result. We further generalize the problem and consider the following weighted sum. Various specific cases of this weighted sum and their associated quadratic forms have been studied by mathematicians in recent years. We studied the particular case of coefficients where, for a given r, the first r-1 coefficients are all 1, and the remaining coefficients are r. Solving this generalized problem, we obtained exact values of L, the minimum number of terms required for universality, for all given values of r, with certain optimal bounds on M. The techniques used in the paper are purely algebraic and combinatorial, but they generate some very nice general results. Thank you for your attention.